new questions.
Okay, thank you. Sounds like I'm coming out of the microphone, or the speaker. This is the microphone. Unlike Jacob, I've never been to Arizona before, though I've actually wanted to my entire life. When I grew up in Iowa and Nebraska and had just terrible seasonal allergies when I was a kid. I was allergic to everything that grows on the prairies, and my mom always told me the only way I could live without those allergies was to move to Arizona. And so I don't know why she came up with Arizona, but I've wanted to be in Arizona my entire life because visiting Arizona represented to me the liberation from all human suffering. So I'm very happy to be here now. I'm feeling really good. I've kind of been asked to talk about Lubin-Tate spaces, and I'm really going to talk about some work that's fairly old, but there's a lot of questions that are of interest to topologists from back then that are still unresolved, and I think with a lot of newer technology, there might be some hope of making new progress on them. And so my main goal is to introduce sort of some of the ways we looked at Lubin-Tate spaces and just to kind of advertise some of these questions that were of interest in topology. One of the things about this is, well, I guess I'll get into it as I get into it. One of the things, though, about me is I always give talks before I write things up because I can't really figure out what I want to say until I'm standing in front of an audience. And that means that the notes that I've put up and will put up may not correlate very well with what actually goes on here, but they'll supplement each other. So let me start with something classical, which is the famous Kronecker-Weber theorem. Am I writing large enough? It's probably just me. Oh, you mean, all right. This is thicker, okay. So the classical Kronecker-Weber theorem says that all the abelian Galois extensions of the rational numbers are gotten by adding a root of unity. So and so after that, there's Kronecker's famous Jugendtraum, which in some ways says that you want to construct all abelian Galois extensions by adding something like the roots of unity. Now, what are the roots of unity? Those are the points of finite order in the multiplicative group, and Kronecker's Jugendtraum was to find other groups and add their points of finite order to make abelian Galois extensions. And this is an idea that's been tremendously developed. So in their work on local class field theory, Lubin and Tate modified this a little bit. And they showed that you can get all the totally ramified extensions of p-adic fields by adding the points of finite order. So let me just say get Galois extensions from points of finite order in formal groups. So let me just say using formal groups. Now, if you don't know, if you haven't looked at the classic Lubin-Tate papers, Formal Complex Multiplication in Local Fields, there is a really beautiful paper. It's really simple, and It's just a very beautiful idea. So I said something about it in the notes. Most of what I said was this paper is a prerequisite, but I did some explanation. But I think in today's talk, I want to focus more on this notion of formal group rather than go through what Lubin and Tate did. So they gave a very beautiful explicit construction using formal groups. So let me say a little bit about what a formal group is or what a formal group law is. Sorry, I guess I was warned. I'm not used to this, so just holler if something's not working right. So what is a formal group law? Over a ring R. Well, it consists of a formal power series in two variables, which it's usually easier to write it like this. It looks like that's x plus y plus higher terms, and it's supposed to be a formal way of adding two things. So it's supposed to satisfy some properties. It's supposed to satisfy the property that x, the usual properties of a group, it's unital, it's commutative, and the hard one is that it's associative. All right, so that's a formal group law, as opposed to, so let me just say kind of very quickly, it'll be important to think about these algebraically, as I've written, and also kind of in geometric or analytic terms. So you can also think of this as a one-dimensional Lie group in some appropriate category. So let me just give you kind of a sort of an ad hoc useful category to work in, and let me call this the category of Lie varieties. That's what Nick Katz calls this in one of his papers. So the category of Lie varieties, or Lie variety, the category of Lie varieties, it's the category whose objects, so over R. So the category of objects are, we'll call them, it'll just be affine n space over R. And I have to tell you what the functions are. So the functions from affine n space to affine 1 space are formal power series in n variables. And the affine n space comes with n projections. So in particular, there's these functions x1 to xn. And that's an isomorphism. So sorry, this pen got away from me. That's an n there. So the nth one is the product of the first, and this now composition is what you think, and this gives you some category of abstract varieties, formal varieties. It's not a very big category, but it's the one, it's big enough for us to work in. So a formal group is a group object in this category. A formal group law is, and a formal group will be, I'll come back to this in a later lecture, but a formal group will just be, we'll just think of it as an abstract group object in this category with a non-canonical identification with AN. So anyway, forgive me, that's a bit sloppy, but I just want to, I'll say this is written up a little more carefully in the notes, but I want you to think about a formal group as a geometric object as well as an analytic object. Okay, so so sometimes I'll use the word formal group law, sometimes I'll use the word formal group, and this depends on whether or not I have a coordinate in mind. Okay, so as I said, Lubin and Tate used the points of finite order in a formal group to generate abelian Galois extensions of fields, and this question comes out right at the beginning. Which is, how many formal groups are there? And so in some sense, and also, how can you construct formal groups? And in some sense, this question has an answer. In some senses has an easy answer. In some sense, the answer is extremely complicated. So one version of the easy answer is the following theorem of Lazard, which says there's a universal formal group, the functor, which sends a ring R to the set of formal group laws over R, that functor is representable. That's representable. It's by ring homomorphisms from some ring L into R, where L is a polynomial ring on infinitely many variables. So if I was to spell this out more precisely, I'd say there exists a formal group law over this ring, and the functor, which associates to a ring homomorphism from L into R. The image of that formal group law over R is that's a bijection between ring homomorphisms from L into R and the set of formal group laws over R. So now, yay, we know all the formal group laws over any ring. They're just in one-to-one correspondence with infinitely many sequences in the ring R. But formal group laws can be, now, how does this, so where do these get retired to? Where?
Like leave the stack, build up a stack on that.
Oh, I see. They can go on top of each other. I didn't think of that. Okay. Okay. That's a polynomial ring. I'm going to try to always be really good about having, the super double brackets to mean form a power series ring. But yeah, that's a polynomial ring. Okay, but sometimes two formal group laws are isomorphic. So what's an isomorphism of formal group laws? So an isomorphism from, say, F to G, well, that'll be a power series, G of X, such that it carries the multiplication in F to the multiplication in G. And we really want to understand the category, or the groupoid, if you want, of all formal group laws, not just individual ones. We want to know when two are isomorphic. And Lazard also produced a universal isomorphism. So I guess that's probably kind of obvious, but let me just say there's a universal isomorphism. And I'll just use symbols S1. So there's a universal, so given two formal group laws and an isomorphism between them, there's a universal isomorphism over this ring that base changes to any given one. Okay. So that, in some sense, gives us an answer to the problem. We just have to take this infinitely many sequences of elements in R, mod out by all the infinitely many other sequences that would form an isomorphism, and then that quotient gives us all the formal groups over R. So that doesn't, that's a picture. It doesn't help us. It's not a very useful picture to work with, but I want to get into it a little more carefully in a minute. Okay, so now let me back out of the of this algebra for a minute and point. And so I said that formal group laws were studied in algebraic topology, and so let me briefly tell you how that happens and what algebraic topologists are interested in about formal group laws. So I'm going to be very brief about this, just so as not to burn all the time talking about this. But so in algebraic topology, we're interested in generalized cohomology theories. Which traditionally go by the generic name E, with Chern classes for complex line bundles. Now, Chern class, so that means to each complex vector bundle over a space X, there's these Chern classes. And they satisfy all the usual properties of Chern classes, meaning they're natural, things like that, and they satisfy the Cartan formula. So there's a formula that expresses the nth Chern class of a Whitney sum in terms of Chern classes of the summands, and they're natural. But there's one property that if you're used to Chern classes in ordinary cohomology or Chern classes in the Chow ring or something, there's one property that doesn't hold in general. So it's not true in general that the first Chern class of a tensor product of line bundles is the sum of the first Chern classes. When you first learn about Chern classes in ordinary cohomology, this is something that this is a property that you use to make a lot of calculations. It's something that holds, but in general, what is true in general, and this is a theorem of Quillen, for general E, the first Chern class of a tensor product of line bundles is, so for general E, there's a formal group law F over the E cohomology of a point, and this is formal power. This is the formal sum of the first Chern class of L1 with the first Chern class of L2. Okay. So, or in the other notation, I would have written that as the first Chern class of L1 plus over F, first Chern class of L2. So this is a surprising, or maybe not a surprising fact, it's an extremely powerful fact. And Quillen also showed that for some cohomology theories, for the cohomology theory of complex cobordism, which is the universal cohomology theory where there are Chern classes for complex line bundles, that this formal group law was Lazard's universal formal group law. And this was always a great lesson. I asked Quillen once how he discovered that, and he told me that he'd been making all these calculations with Chern classes in complex cobordism, and he kept getting contradictions. And then he finally realized that he was assuming that the first Chern class of a tensor product of line bundles was the sum of the first Chern classes of line bundles. And then this is like a stroke of genius. He was like, well, that's obviously wrong. How wrong could it be? And then he just guessed that it had to be universally wrong. That's what his theorem says, that like it's not just wrong, it's as wrong as it could possibly be. So that's a good lesson. When you make a mistake, assume it's just the worst possible mistake in the world. Now, this leads to an amazing connection between formal group laws and algebraic topology, and I'm going to write something down now. I think I want a picture up. Forgive me, I'm going to move this so I can put a picture here. This eventually leads to an important spectral sequence in homotopy theory that goes from the cohomology of something I'll write like this, which is this MFG stands for moduli stack of formal groups with sections, coefficients in a line bundle, and it converges to something about the homotopy groups of spheres. Okay, so what is this MFG? This MFG is this, you can think of it as a category or the quotient of a big space by a big group action. The space is Lazard's space of infinitely many sequences of elements in your ring, or formal group laws over the ring, modulo isomorphisms. And we're going to come back and meet an object like this in concrete ways later. So I just want to get a geometric picture up now. And this omega is the dual of the Lie algebra. So it's it's the space of invariant differentials on the formal group. And again, we'll also do this more concretely later, but I'm often going to jump back and forth between thinking of a formal group as something algebraic, written in algebraic formulas, and something as a group structure on a line, and in which I can think about in geometric terms. So there's this kind of picture here where I have this moduli space, which is really kind of an orbifold. And over this, I have this bundle of groups. So these are formal groups here. And each of these fibers has a group structure, and it has an identity element, and then there's a tangent space at the identity. There's its dual, and that forms a line bundle over this moduli space. And we're interested in topology and the cohomology of the sections of that line bundle. So we're studying the aggregate of all formal groups. Okay. Okay, I think I'm doing okay. So how do we think about this whole moduli space, and how do we think about that cohomology? Maybe before I get into that, let me just emphasize that in topology, we're interested in this in kind of an element by element way. I mean, when you need something about the homotopy groups of spheres in a problem in algebraic topology, you need to know, you often need to know, well, what is pi 73 of something? That's a product of a cyclic group of order 14 with a cyclic group of order, 2 and 7 and whatever. It's a product of groups. What are the generate? You have a very element by element relationship with it. And so the information that's kind of come out of algebraic topology in connection with this tends to be very computational and very kind of element by element understanding. It doesn't mean we don't think about this from a conceptual point of view, but everything ultimately kind of comes down to some very computational and, as I said, element by element approach. Okay, well, I haven't really given you a single example of a formal group, and I haven't even told you what the formal groups all look like, and I haven't gotten into Lubin-Tate's second paper, which is about the deformations of formal groups. So let me try to. I know this cricket's going to chirp, but can whoever's making that cricket chirp tell me how much time from now it will be before the cricket chirps?
26 minutes.
What's that? 26 seconds? Oh. Okay, good, good. So let me give you some examples of some formal groups, okay? So here's an example of a formal group. There's the additive group, and it's got formal sum x plus y. So that's not an infinite sum. There's another one, which is the formal multiplicative group, and we usually write that as x plus y minus xy, but that's because secretly you've taken 1 minus everything and multiplied. So this convention for doing this comes from what happens with Chern classes. So here's two different formal groups, and let's ask the question, are they isomorphic? Well, if I'm over a ring of characteristic 0, one isomorphism would be to take 1 minus e to the minus x, right? If I take, I'm just guessing this. I'm going to guess that produces this formula, but that might be wrong. But that probably takes g of x plus y, maybe, g of x plus g of y minus g of x times g of y. Maybe that works out. It doesn't really matter. Some minor variation on that will work out. And in fact, that's great, except I had to be over a Q algebra because I had to have denominators. So that's great. Over the rational numbers, they're isomorphic. Are they isomorphic over the field with P elements? Well, here there's a good observation. Let's suppose, in fact, are there even homomorphisms between them? So let's look at, let's suppose we have a homomorphism, let's say from the additive group to the multiplicative group, and we're in characteristic P. Well, that's supposed to be a group homomorphism, so g of x plus itself P times is supposed to be 1 minus g of x to the P. So, okay. All right, now what is that? Well, I'm in characteristic P, so one of these is 0, and by convention that's 0, and the other one is going to be by Frobenius, whatever, that'll be g of x to the P, right? Which is, if I was over a field, let me write that as g Frobenius of x to the P in case g had some coefficients that were not in characteristic P. Well, right, this means that g is equal to 0, at least if the Frobenius is an automorphism. So that means that g is equal to 0. So in that case, there's no homomorphisms from the additive group to the multiplicative group. Now, this leads to an important invariant of formal groups in characteristic P called the height. And let me so I wrote up proofs of a lot of these things in the notes. Maybe this one's an exercise. Just in the interest of time, I think I'll just state it here. So the theorem is, so now suppose I'm over a field. Suppose we're over a field of characteristic, of positive characteristic, and I have a homomorphism from two formal groups. Okay, so I have so the theorem is there exists a unique g of x with g primed at 0 not equal to 0, so a unit. And Q, which is some power of P, that's supposed to be an A, such that f of x is g of x to the Q. Okay, the idea is you look at the derivative at 0. If f doesn't already have this property, its derivative at 0 is 0. But there was a group homomorphism, so that means its derivative everywhere was 0. So that it means it was a function of x to the p, and you just iterate. So this a might be infinity. So this a could be infinity, and we call this the height of f. So a is the height of f. And the height of a formal group is, by definition, the height of multiplication by p. Okay. So I exploited that in this previous calculation. The height of the additive group is infinity, and the height of the multiplicative group is 1. And so they weren't isomorphic. Now there's a cool theorem due to Dieudonné, which says that if k is, let's say, separably closed, k is perfect and algebraically closed, then any two formal groups of the same height are isomorphic. Okay, so we had this giant space, right, this MFG, this giant space of all formal groups and all isomorphisms between them, and yet if I looked at the points of that over an algebraically closed field of positive characteristic, there's just one point for every height. Any two are isomorphic. So there's something weird about the structure of that space or that stack that we're not really kind of thinking about when we just think about it as an infinite product of copies of the ring R. Okay, so the next step. So I'm not doing Lubin and Tate much justice in this talk. In the notes, I explained a lot more about Lubin and Tate's contribution here. But so Lubin and Tate. So now we know the things in characteristic P. Now let's try and deform away from characteristic P and see if we can understand all the deformations. And that's the Lubin-Tate deformation space I'm about to tell you about, and it appears in their second famous paper called Formal Moduli of One-Parameter Lie Groups. So how does that go? So let me So Lubin-Tate deformation spaces. Okay. Okay, so, all right. So I want to consider the following setup. I have K is some field of positive characteristic. And I have a formal group gamma. So over K, I'm going to typically call my formal groups gamma. So gamma is a formal group law over K. And I want to understand, so I know gamma, it's determined by its height, and I want to understand what happens over other rings. So we look at rings B, which are either complete local rings, or it's a local ring, and you can assume the maximal ideal is nilpotent, or if you want to think about topologies, you can imagine that it's complete with respect to the powers of the maximal ideal. So I'll just say this is a complete local ring with maximal ideal M. All right. Now, a deformation of gamma to B is the following data. I won't write it out so formally, I have a formal group G over B. So I have B mod its maximal ideal. So let's call this map R for lack of a better name. So the data is a formal group, a map here. So the data is G, I, F, where G is a formal group over B, I is a map to here, and then down here I have an isomorphism of G with gamma, with gamma based, regarded as a formal group over B mod M. So that's a deformation, and then a map of deformations is the obvious thing. A map of deformations will be an isomorphism of the G's that's compatible with all this information. And so that makes a category we might as well call def orm. Let's call that deformations of gamma applied to B. So that's a groupoid. Now this isn't just a random groupoid. So this is another useful exercise if you're just getting acquainted with formal groups. In fact, this is what's called a codiscrete groupoid. So any two elements there's at most one map between any two elements. So if I have two deformations and there's at most one isomorphism between them. Two maps of G between formal groups over B that induce the same homomorphism mod M actually are the same. So that's kind of a fun little exercise to think your way through. But so this is a groupoid. It's actually a codiscrete groupoid, and I might as well replace it by what you might call pi 0, which is just the set of isomorphism classes of objects. It's just equivalent. It's equivalent to that set as a category. So there's not a lot of information in the morphisms in this category, and the amazing thing about Lubin and Tate was that they determined this set. So let me just say theorem due to Lubin and Tate is that I'm going to say this in a kind of a cruddy way. That this is just, so n is the height of gamma. So this is just a product of n minus 1 copies of the maximal ideal. So that's the second. Lubin and Tate wrote these two extremely influential papers in the 60s. One was about constructing local class field theory using formal groups, and they gave a very beautiful construction of formal groups. And the other was they studied all the deformations of formal groups. So this gives you a different picture of the aggregate of all formal groups. You could start with one in characteristic P and maybe deform it through other rings in characteristic P and then deform it up to characteristic 0. And every time you know that there's only n minus 1 of these deformation parameters. So what's left? What's left to look at? Doesn't this just solve the whole problem about classifying formal groups? Well, it doesn't, because there's still a sense in which some of these are the same. If I had a deformation of gamma and another one, now I would know whether they're isomorphic by an isomorphism covering the identity map of gamma, but I really just want to know if they're abstractly isomorphic. So I want to mod out by the equivalence relation that consists of isomorphisms which don't necessarily cover the identity map of gamma. So we can say that in this way. Is this up if I point? I can point here. I'm allowed to point here. So in this picture, there are some more things acting. The Galois group of K, the field automorphisms of K is acting on this set, and the automorphism group of gamma is acting on this set. And what we really want to understand this set mod the automorphisms of gamma. We want to understand this as explicitly as possible. Okay, so I was going to write this out, but just in the interest of time, I think I'll just say this part in words. So in algebraic topology, we could approach the homotopy groups of spheres by understanding something about some kind of cohomology of the moduli space of all formal groups. And this Lubin-Tate theory gives us a way of decomposing that moduli space into this, which I'll make more precise in a minute. But this has to do with the structure of just some group we might work out in advance, acting on some n-1 parameter space. And so there's a way of taking the cohomology groups we were interested in and writing those in terms of the cohomology of gamma acting on something. And that corresponds algebraically to an approach to understanding the whole moduli space of all formal groups, but it also corresponds to a decomposition in homotopy theory itself, and that's the field of chromatic homotopy theory. And so this study, Lubin-Tate spaces, there's an intimate relationship between questions about Lubin-Tate spaces and questions in chromatic homotopy theory. And the questions that I want to advertise today and then in the course of these lectures come from these problems in chromatic homotopy theory. Okay, well, let me just push on with this. So I didn't state this in a very good way. I just said for every ring B, this is isomorphic to this. Well, I should have said this is really naturally isomorphic to it, and if it's naturally isomorphic, then I could take B, I could take the universal example of such a B, and so, in other words, they construct a universal deformation over the ring of formal power series in n-1 variables, where W is the ring of Witt vectors of K. They construct a universal deformation such that any right, so the set of appropriately continuous ring homomorphisms, well, I guess not even that, the set of augmented or something ring homomorphisms from this to B is the set of n-1 tuples of elements in the maximal ideal. It's just determined by where the UIs go. And so the real statement is, what they really do is they construct a deformation over this ring with the property that this functor is represented by ring homomorphisms from this formal power series ring. Now that's kind of nice because I talked at the beginning about working in this space of formal Lie varieties, and so we were picturing our groups living in that category, but the Lubin-Tate deformation space itself, the universal, it is also a formal Lie variety. And one of the things I'm going to do over the course of this lecture is study this through geometric means and try and understand this action. Okay, so let me see how I'm doing. I think I'm about where I want to be. So in topology, we give this ring a name. We call it E0. We put an N in there, but I'll just... and that's the even part of a graded ring, which we call E star. Where for historical reasons, this is an evenly graded ring, and this has degree -2. And the Lubin-Tate theory gives us a map, so we call aught gamma, that's usually written as Sn, And in the topology world, that's called the nth Morava stabilizer group. And this acts on E star. And if you want, that's the module of sections of the Lie algebra of G. So anyway, I'm just putting this up so I can state some things more clearly. So in topology, in algebraic topology, we're interested in the cohomology of this group with coefficients in this ring, or more generally, and we have a lot of questions, a lot of things we would like to know about that. So just, I want to advertise, so as I said, I wanted to get some of our interesting questions out. And there's a lot of things that we know about this from the point of view of just explicit calculations that would be really great if we understood from a more theoretical point of view. So, I'm sorry? Yeah, in height n, I have n minus 1 deformation parameters. I'm sorry, who asked?
So it's Sn minus 1.
No, Sn, so gamma had height n. So if when it has height n, there's only n minus 1 deformation parameters. So we call, I'm sorry, I lost, who was asked?
So the action is not
Yeah, exactly. I'm glad that was a great question because I was going to write that exact question down. So here's some fundamental questions in algebraic topology. So fundamental questions we're interested in. So can one okay. Is there anything else you'd like me to declare that it's not? So.
We also thought that was unclear over here, so we're happy with that.
What's that? You were confused by that?
Also, we're discussing interjecting with the same comments.
Okay, well, we don't have to call it that. We could just call it aught gamma. Okay. So can one write down explicitly the action of aught gamma on this ring? So this has, in some sense, there's a surprisingly, this is hard. And in fact, I was looking through some of Jared Weinstein's notes when on some of his lectures on Lubin-Tate spaces, and he thinks of this as, he indicates this might be something humans were just not meant to know. And that could be, but we're here in Arizona, free from human suffering, and maybe we can know that here. And I think that, but so the answer is that we do know this fairly well, and that's really one of the things I want to talk about is this crystalline period map that Dick Gross and I constructed quite a few years ago that gives you some version of the action. And another thing I want to talk about is a theorem of myself and Mike Hill and Doug Ravenel that says you do know this explicitly when not for aught gamma, but for any finite subgroup of aught gamma. So I'll explain. So one of my goals is to really explain what you can say about this and how you can understand this action. So that's one thing. Another thing that I want to, that for various reasons, I'll describe later. What is the Picard group of Lubin-Tate space? So that's H1 of aught gamma, also not the symmetric group, with coefficients in the group of units in this ring. So there's a conjectured answer for this, but I know that Cricket's about to go, so I'm not going to write down. There's a conjectured answer about this that's known when n equals 2. So conjectured answer and maybe primes greater than 5. And in one of the projects, I guide you through that calculation. And there's a reason I want to do that, because I think if you're going to work on this problem, but I get to ignore. Okay, well, I was just going to go like that. Oops. That's sort of, no, not in Arizona. I wouldn't do that, I'm sorry. I'm just going to wrap it up here. So there's a conjectured answer. The conjectured answer is that it's topologically generated by two explicit elements. And I'll explain why we think that's true. And we know the answer to that at height 2, but I don't know of any theoretical way to approach that. And I think the only way is to dig in there, but there are some very compelling patterns in the calculation that eventually leads to this. So in one of the projects, it's a little tedious, it's largely bookkeeping, but I've summarized what you need to assemble this calculation and kind of guided you through it. And I think that if you're going to do this, you have to kind of dig into that calculation and really try and understand it. And look at it that way. So I've kind of tended to make the project aspect of this a little more formula-based. So there's also a project about explicitly understanding this for certain finite subgroups. So here's another observation that's somewhat a miraculous observation. And that is that in height 2, the map from the cohomology of Sn with coefficients in the constant functions on Lubin-Tate space to the cohomology of Sn with coefficients in all functions on Lubin-Tate space is an isomorphism. So that's a really surprising fact, and at primes greater than 3, that's due to Shimomura. And I'm not 100% sure. Let me just say at primes less than or equal to 3, it's probably due to Agnes. Beau. No, that doesn't look right. How do you spell it? Oh, it is. Okay. And I think Irina Babkova. I'm not sure who all might have contributed to this. Maybe Mark Behrens, maybe Hans Werner Henn. I'm not 100% sure. In fact, I was trying to call Agnes right before my talk to find out if it's even true for primes less than or equal to 3, but I think it is. Anyway, this is really another remarkable fact, and I don't know if this is true for n greater than 2. Okay, I think, so these are some questions that we're interested in that I'm going to talk about as the time goes on, and maybe I'll just, at the end, I'll just say a little bit about where we're headed without writing it down. So you can go a lot of distance by replacing the ring of formal functions with the ring of entire p-adic analytic functions, meaning p-adic analytic functions that converge on the entire p-adic analytic plane. And in that case, the group of line bundles, in that case you can sort of understand the action. And there's an étal map that Dick Gross and I constructed down to a projective space of dimension n-1. There's a lot to say about that map, and I just, because the cricket's gone, I won't say any. I'll try to say stuff at the last lecture. And the group of line bundles for the formal scheme and the group of line bundles for the analytic thing are the same. And so the problem of computing the Picard group is a problem in analytic geometry where you have this quotient to projective space, and then you have these, what are, I guess are being called the two towers now, that relates this to a problem about GLN equivariant line bundles on the Drinfeld upper half plane. So the possibility of that, of describing line bundles from those 2 points of view has been around for a while, and no one's ever been able to do anything with it. But I think we were always hampered by not really knowing in what sense how to pass between those. I think that's something where the technology now is a lot better. Anyway, so what I'm really going to be doing over the next several lectures is starting with some formulas and eventually explaining to you the theory of the crystalline period map and that geometric picture of how this acts. Well, I've gone over time, so I'm going to stop now and I'll just pick things up next time.
Maybe we have a minute for questions. Yeah, this is. Here you go. Yeah, it's for the recording. Thanks.
So, I might just be a little bit confused, but is it like, does it just follow from the universality that the automorphism group of this deformation ring W of U1 to UN modulo its maximal ideal should just be in bijection with odd gamma? Because doesn't that just follow from the universality?
So, sorry, so that W of U1 to UN minus 1 is a ring representing a functor. Right?
Yeah, so like if you go modulo its maximal ideal, and if you look at like automorphisms of that, shouldn't that just be in bijection with odd gamma? Is that correct?
No, gamma is acting on, I'm not sure.
Okay, anyway, sorry.
Yeah, thank you. I appreciate the question. I think I'm not quite getting it, and maybe we can talk. But I'll say, so gamma is a formal group living over this mod, the maximal ideal, and the automorphism group is acting trivially mod the maximal ideal, but it's acting very non-trivially on the ring. But come talk to me.
Sure.
Yeah.
Okay, let's thank Mike again and adjourn for lunch. We'll start again at 2:20 sharp.